it always worked for the best, but it just the IP issues was wasting a lot of time with the lawyers. As I said, selective but intimate. So here's a success story that I always brag about, even though it was a few years back. We at Hewlett Packard looked at something like that and discovered that optics and optoelectronics should be everywhere, in displays, interconnects, life sciences, electronic the communication equipment. So we identified optoelectronics as a very, very important discipline. And we looked at what optoelectronics did for us. We created like a $6 billion lightweight measurements product line based on optoelectronics. And we looked at the computers, look at what DVDs and optical memories and displays for computers. And then we went to communications and we looked at optical interconnects. How can we replace a couple lines inside computers with faster technology? And light was the most important option. And we kept doing that for biotechnology. It is impacting us too. And for the combination of nano and bio. So optoelectronics was identified as a very important discipline for us. In 1990, early 90, what was the best university, and still is, in optoelectronics? We looked at many universities who were very close to Stanford, but we identified that UC Santa Barbara was able to get the best team together. And we were trying to move the company from an instrument company to a computer and communication company. And we looked at the problems that matter that we want to solve, and we looked at our technologies that are needed to solve those problems, and we found a big gap in our portfolio. We need a laser source that looks like an LED chip. You can make a large number of it, but it acts as a laser. And that was the solution to many of our problems. We were really surprised by what the computer people told us. That was in 1990, and they were predicting that the PC would be $1,000 in year 2000, which happened actually, about $1,000. The communication card would be no more than 10%, like $100. So if you go from 100 megabit to 1 gigabit, you should only build a card that will cost about $20. And if you have 10 lasers and waveguides, fiber, and all of that, we ended up requiring the laser to be 25 cents. And there was no laser that was made for 25 cents in 1990. So that was the most important problem that we needed to solve. We started a program, and I have to give the credit to S.Y. Wang, who really looked at that and made this prediction and put his career on the line that we need a source. And we looked around and found Dr. Iga in Japan, who invented the vaccine, and came and said, we have to build the vaccine. In fact, it happened during the earthquake, 1989, that our building was twisted and demolished, and we lost most of our equipment. And we were supposed to go to a conference there. Of course, we canceled all our travel. But he did it on his own and went and lived in Japan for $10 a night. I didn't know that in Japan they have these coffins that you go out and you sleep overnight for $10. And he came back with a project outline. And he worked out the details and how much money we want. It was prohibitively large. We couldn't do it. So we worked out the various alternatives, and the decision was made that we have to deal with a university to help us with that. And that was the best thing we did. We worked with Larry on the shortwave lens, and with John Howard on the long-wave lens. And I have to tell you that spending 2 years doing a conference call every 2 weeks with a professor and their team was the reason we were able to. The last count I saw, I think the companies I worked for produced 1 billion vaccines. So it was, that's a large volume. I'll tell you where it went. But it was very, very important for our interconnect product line. It looked good at 1 gigabit, looked good at 20 gigabit. We want to replace all those copper lines with a small, tiny device, which we did. And we worked on government, Department of Defense contracts with UC Santa Barbara and other universities. And when we went into the gigabit Ethernet. So at that time, there was something called gigabit Ethernet and broadband and fiber to the home. But the problem was you can't dig the streets and have the fiber in the streets. So we worked with this company that found a way to put fiber in the sewer system. Every time they replace the sewer system, you just put 4 fibers. And the gigabit Ethernet comes out from the other side. That's why we call it and actually, in the city of Santa Clara, that's what happened. Now, every time you break a sewer system pipe, you have to replace it and put 4 fibers in it. All of those have VCSEL. And this is a product line that we built based on the vertical cavity surface emitting lasers that came from the interaction we had with UC Santa Barbara. Now, okay, I'm going to skip this one. What was the step after that? We found people coming to us within the company, finding more applications for this laser. In fact, the first objective, that last slide that I showed you, that was a small part. That was like 100 million pixels, that's all. But then it wasn't until someone in the lab invented the optical mouse that I think everybody is using that. If you go to Fry's Electronics, there are no ball mouse at all. It's all optical mouse. And he uses an LED in it. And that was invented in 1995 at Hewlett-Packard. And what's inside the optical mouse? There's no real mouse inside, but there is an optical system, like as you see on the right-hand side here. And it worked very well until another problem that mattered was ahead of us. All the furniture company were polishing their furniture so smooth that the LED didn't work on it. So the return of those optical mouse started to get larger and larger. So 2 engineers said, wait a minute, don't we have this VCSEL and we can change the optical design, we can penetrate more into the surface. And that's when we came up with the laser mouse. And now if you go and buy a mouse, actually you don't see the optical mouse, all you see is laser mouse. So that was the thing that sold at $1 billion. We have to set up a whole facility in Singapore to build our vertical cavity surface emitting laser. It was a big thing. And throughout this interaction with the university, we solved a large number of problems. Here's the inventor, Gary Gordon, and he invented the optical mouse. I don't have a picture for the guys who invented the laser mouse in 2002. But it was a very good project for us. Many other projects followed. Once you have a good success story with the university, it just leads to others. And to me, the professor is either motivated to work with you all the time or just not. And as a suggestion, if it doesn't work for the first few years, just stop it and go to another group. You're lucky to be able to. But I think the best thing that we did is that we hired those 48 PhDs from UC Santa Barbara over the years, and that helped the company tremendously. I see the engineering schools going into multidisciplines and interaction with disciplines. I think most of the problems that we tried to solve were not single discipline. It's a combination or intersection of nano, bio, and optical sciences. And Santa Barbara has all of that. Stanford has that too. This is a picture of what Stanford is planning and building. Those 4 buildings, biotechnology, environmental, which is done, nanoscience, and information technology, is an example of where the cross-discipline is happening. A few words about the innovation, as Leslie mentioned that. Where we are coming to universities for good students. You start with a good project, you work with a PhD student or a master's student, and throughout the product is a good interview during this interaction, and then you hire them at the end. But you need to hire very independent people who never ask that question. And so what does it take to innovate? This